Hello, in this workshop, we're going to be creating an Omni-chain swap contract that will let users swap tokens between connected chains. So it will allow users, for example, to swap ETH or ERC20 tokens for BTC or Matic. So let's get started. First of all, we're going to be cloning actually a GitHub, a template for ZetaChain that is hosted on GitHub. So if you type git clone GitHub ZetaChain /template and clone that template, you will get a new directory called template. Let's check it out. It's pretty empty, just a bunch of config files, but if you type yarn or you can use npm, it will install all dependencies, and this is a hard hat based template, so you will get all the tooling installed automatically. Now if you type npx hard hat, you will see all the standard commands as well as additional commands that were imported from ZetaChain's toolkit, like balances, cctx, and faucet. So before we start, it's useful to create an account. I already have one in this template, but if you don't, type npx hard hat account, it will create a new account for you. And if you want to save it, just type save and it will create a new account and store it in a .env file. So you can, so hard hat has access to it. So once you did that, you might want to check your balances. So balances command will query all the balances on all the connected chains and show it to you in a table. Make sure that you have tokens on ZetaChain as well as on at least one of the connected chains. For example, Girly. In our documentation, we have links to faucets you can use. Okay, to get tokens on ZetaChain, you can use the faucet command that we have here. So it will ask you to confirm on GitHub. I'm not going to do that right now, but once you do, tokens will be sent to you. Okay, cool. So now we want to create an Omnichain contract. So what is an Omnichain contract? A contract is considered to be Omnichain if it's deployed on ZetaChain and it inherits from Z contract and it implements a function called on cross-chain call. And this function gets called whenever users send tokens to a TSS address on one of the connected chains. So basically, it's a regular Solidity contract that implements a certain function that can be remotely called from other chains. So to create a contract, we can use the tools we have from the toolkit, and the command is called Omnichain. So it just accepts a name and arguments, and the arguments are the values that you pass from a connected chain to your Omnichain contract. So for example, if you want to swap tokens, you need to pass the token address that you want to get and the recipient, right? That's the only information you need. Everything else is accessible automatically, right? So if we want to create a swap contract, we can just pass two arguments. One is going to be the target token address and the other one is going to be your recipient. So let's do that right now. The first argument is the contract name, then we're going to pass target token. By default, arguments are strings, but we know that the target token will be an address, so we can pass an address. And recipient, we're going to leave it as is, even though for EVM chains, recipient is an address, but Omnichain contracts also support Bitcoin. So we're going to see in a minute why we want to keep it as string. We're going to change this in the source. Okay, so when you run this command, you will see that three new files are created. 2 tasks for deploying a contract, 1 for interacting with the contract, and the contract itself. The contract is pretty straightforward. It's boilerplate code, but it includes some useful logic for decoding a message. So you can see that it's just basically one function called onCrossChain call, and it accepts 4 arguments. One is context, which is useful because it contains chain ID. Address is the ERC20 address of the token that you're sending to the TSS address, effectively depositing it into to ZetaChain. Amount is the amount of tokens, and the message is the data that you pass from a connected chain to your contract as arguments. So from EVM chains, that would be in the data field of a transaction. From Bitcoin, that would be in a memo. Okay, so first of all, let's dive into the onCrossChain call function and see what we need to do. We're going to have 2 values, right, that we need to extract from the message. So we're going to have target token, so target token address, and it's going to be of type address. We're also going to have a recipient address. Recipient address for EVM chains is of type address, but we also need to make sure that our contract is capable of swapping to Bitcoin. And for Bitcoin, that is a batch32 address, so we can't store it in an address variable. So let's use bytes memory for that. Now we need to take into account that a transaction might be coming from either an EVM chain or from Bitcoin, right? So right now, as of this moment, ZetaChain supports 3 EVM chains, Ethereum, Polygon, and BSC, and 1 non-EVM chain, Bitcoin. So let's execute different logic based on the chain that this transaction is coming from. So we're going to be using the context argument and the chain ID property, which returns an integer chain ID. So if it's Bitcoin, and let's define this as a constant so it's a bit easier to see, right? So it's going to be Bitcoin, and the chain ID that ZetaChain uses for Bitcoin testnet is 18332, and it's an integer. Okay, this makes it a bit easier to read. So if the transaction is coming from Bitcoin, then we need to process it and extract value. We can't use ABI decode because we want to make sure that the data coming from Bitcoin is as compact as possible, and we format it manually. So the way we do this is we use the first 20 bytes of the message for the token address, right? So we're gonna have a memo coming from Bitcoin with first 20 bytes as the target token address and the following 20 bytes as recipient address. So for EVM addresses, 20 bytes is sufficient, so that's good, right? So we need to manually decode. Thankfully, we have some helpers we can use. So we have this library called bytes helper lib, and this lib contains a function. I mean, you can check it out. Let's actually look where it is. So in ZetaChain's GitHub, you can open a toolkit repo. So let's just go to the toolkit repo. And this is installed automatically, so you don't need to install it, but it has a contracts directory with bytes helper lib, and it has some useful functions that we can use, right? And one of them is bytes to address. So we're going to use that to extract value from the message, and the argument is an offset. We don't need an offset because it's the first value, right? Let's import bytes helper lib from ZetaChain toolkit. It's in contracts and bytes helper lib.sol. Okay, so what this will do is that it will parse the first 20 bytes and convert it into an address. Let's store this value in the target token address. So now we have our target token address. Next, we need to do the same for the recipient address. So we're also going to use bytes helper lib bytes to address message, but we're using 20 as an offset because we already parsed the first 20 bytes, right? So it's the same function, but we're using it 20 as an offset, and it will return an address. What we need instead is actually a byte array. So we can use ABI encode packed to convert this address into bytes and store that in the recipient address variable. So this is going to be just bytes in the recipient address. Cool. So we handled this process for Bitcoin. And again, when a user wants to call this contract from Bitcoin, what they do is they send a native Bitcoin transaction on Bitcoin to a special address called TSS address, and they include the necessary arguments in the memo. In our case, that would be a target token address and recipient address. For example, if you want to swap Bitcoin for BTC for ETH, you would look up the ETH ZRC20 address and use that as the target token address. So it's the token you want to swap for. Okay, we handled the Bitcoin scenario. Now let's process transactions coming from EVM chains, and they're all the same. So we're just going to be using decode address and then bytes. Again, we're going to be passing these as bytes, so we need to specify the type correctly here. So the first is going to be of type address, and let's say target token, and the second one is bytes memory recipient. Okay, we've got these temporary variables. Now let's assign these to the variables we have in the up here, right? So target token is going to be target token address is going to be target token, and recipient address is going to be recipient. So at this point, we should have handled both cases, right? So if it's coming from Bitcoin, we execute this logic. Otherwise, we execute this logic. Okay, some formatting here. Cool. Now what we want to do is we want to actually implement the swapping logic. So at this point, we already have all the information we need from the message. So we're going to be using the swap helper lib, which again contains some useful functions. And the way it works is on ZetaChain, we have internal liquidity pools running on instances of Uniswap. So every supported token has a pair with Zeta, and we can use these pools to swap between ZRC20 versions of different tokens, and that's exactly what we're going to be doing right now. So let's use swap helper lib do swap helper function. So swap helper lib do swap, and we need to import it from the toolkit. Swap helper lib. Okay, so do swap accepts these arguments, and we're just going to pass them so first argument is the token address of Zeta. On ZetaChain, we have a contract called system contract that contains all these variables that we need. So if you type system contract, we can use wzeta contract address. The second argument is Uniswap factory, so system contract contains that as well. Uniswap v2 factory address. The next one is the router. Okay, so it's already pre-filling that. Then we need the ZRC20 token, which in our case is going to be in the argument here. So you can just pass that, and it will pass the address of the token that you're depositing that you want to swap. Next is amount. We already have an amount as an argument for cross-chain call. Next is the target token address, and this is the token address we have here. And the next is min amount. We're just going to use 0 for now. Okay, so this function will do the actual swapping, and it will output the amount of tokens that we got. Let's store it in output amount, and that's going to be of type uint. Okay, so now we've swapped the tokens. Next, we need to withdraw them to the chain that they originate from. So if we swapped BTC for ETH, we need to withdraw ETH to Ethereum. Depositing tokens right now is free, but withdrawing will charge you a fee, because for a TSS address to send tokens to the recipient address, they need to pay, essentially validators, the protocol needs to pay a fee to transfer these tokens. So that's why ZetaChain is charging you a cross-chain fee when you want to withdraw something. So before we proceed, by the way, if you're interested to learn more about system contract, you can find more information in the docs, but also if you go to the protocol contracts repo, you can find the system contract in the ZEDM directory here and learn more about what kind of data it contains and what it can do for you. Okay, going back, we need to calculate this withdrawal fee, and we have this interface I0C20 that has a function called withdraw gas fee, and it will return the cross-chain fee that you will be charged, and it needs target token address. So this returns two arguments. One is gas ZRC20 of type address, right? So it's the address of the token, and the next is the actual gas fee. Okay. Next, we need to actually do the withdrawal. So we also use I0C20 target token address, and we're gonna call withdraw. But before we withdraw, we actually need to approve the transfer of these tokens, of these ZRC20 tokens for gas on ZetaChain. So we're going to do the same, but with approve and gas fee. So we need to approve the gas fee, the transfer of gas fee on ZetaChain. And once we do that, we can actually use the withdrawal. So withdrawal is a function of the ZRC20 contract. So you can call that as a holder of ZRC20, you can call withdrawal and withdraw tokens from ZetaChain to a connected chain. So it accepts two arguments. One is recipient address in bytes, and it's very convenient that we already have it in bytes, right? It doesn't matter which chain you're withdrawing to, EVM, Bitcoin, it's gonna work both if you store it in bytes. And the second parameter is the amount of tokens, which is going to be the output amount minus the gas fee. So this way we will be withdrawing the amount of tokens but minus the gas fee. Cool. Okay, it seems like we have a typo here. And okay, we made a small mistake because approve, you can actually check it out in the protocol contracts as well. So in zrc20.sol, you can see the approve, and it actually needs two parameters. One is the spender, and the second one is the amount. So for the first argument, we're going to use target token address, and yeah, this is just unused argument. Cool. So this should do the trick. Let's check it out in the terminal and compile the contract. So we're going to use an npx hardhat compile to compile the contract. Seems like it was compiled successfully. And we're almost ready to deploy it to ZetaChain, except we need to do one more thing. So the interact task by default right now assumes that you're going to be dealing with EVM chains. So to make this, to modify this task to be compatible with Bitcoin, we need to make some changes. And the changes revolve around the recipient. As you remember, we're not passing it as a string or an address, but rather as bytes. And for Bitcoin, that would be we need to take the Bech32 address and convert it into hex, right? So we're going to have a recipient that is different from just the value that we pass on the CLI. So first of all, we again need to kind of execute a similar logic. Like if it's Bitcoin, then we do one thing. If it's not Bitcoin, then we do something else, right? So to determine if the recipient address that we're passing is a Bech32 address, we're going to be using Bech32 library. So import Bech32 from Bech32. Okay, and in the condition, we're going to check if Bech32 can decode the recipient that we're passing on the CLI. If it can decode, then it's a valid Bitcoin address, so we're going to be using that as our recipient, right? But we need to take this Bech32 formatted string and convert it into bytes. So for this, we're going to be using utils package of utils of the ethers package and solidity pack function. We need to convert it into bytes, and to do that, we're also going to use utils to UTF bytes and recipient. So this will convert recipient to bytes and pack it as a proper argument. If it's not Bitcoin, then we're going to use it as is. Well, first of all, let's import utils from ethers. This decoding process will throw an error, so we need to wrap it in try-catch block. So if it's an error, then it's not a Bitcoin address. So we're just going to use recipient as is because we're assuming it's an EVM compatible address. Okay, so once we have that, we've updated bytes here. This should be ready to go. So make sure that you have Zeta tokens on ZetaChain ready. And once you do have all the right tokens, let's compile the contract again. Don't need to, but let's do it anyway. Compiles, and now we can deploy. So we're going to use the deploy task, not going to modify it at all, just specify network as Zeta testnet. So Omnichain contracts, you only need to deploy once on ZetaChain, don't need to deploy it on connected chains. Execute the deploy task. Once it's finished, you should have a contract deployed on ZetaChain. Okay, we can see that. And now we can actually interact with this contract. Well, first of all, let's actually see it on BlockScout. If you go to blockscout.com, you can paste the address to your contract here and see that it's successfully deployed, which is good. Now we can actually interact with it. So let's try swapping from Gurley testnet to BTC, and for that we'll be using the interact task that we just worked with. So the interact task accepts a set of arguments. First of all is the amount of input tokens. Let's just put a small amount. The second one is the contract. We can copy and paste it from the output. Recipient is going to be a Bitcoin address. So to get our Bitcoin address, we can again use the balances command. It will show you all the balances and also the address. So it's very handy. You can just copy and paste it from here. So this is your address on Bitcoin. You can paste this as recipient, so it should decode it correctly. And we're specifying the network that we are broadcasting this transaction to. In our case, that's Ethereum testnet. And one last argument that we need is the target token. So for this, you actually need to go to documentation. So zetachain.com/docs, you go into the testnet and look up the ZRC20 token address of the token you want to swap to. Of course, in a front end, you can do this. You should do this automatically. But for now, we can just copy the Bitcoin ZRC20 address from here and paste it here. Okay, it seems like we have an error. Let's check it out, what happened. In the interact task, let's check that everything's working correctly. So if it's a Bitcoin address, we decode it, and yeah, we forgot to store it in recipient. So it decoded but didn't know what to do with it. Okay, let's try again. So right now, what is happening is a user sending a transaction on Gurley with values in the data field to a TSS address, and we can check it on the Explorer right now. But before we do, the toolkit has a very useful command called cctx, and you can pass either a transaction on a connected chain or a cross-chain transaction and it's just going to start looking for this transaction on ZetaChain. While it's looking, let's go to Goerli and look up this transaction that we broadcasted. You can see that it was broadcasted 30 seconds ago, and this is the value, right? So the first 20 bytes of the data is the Omnichain contract address, so it should match the contract that you deployed to. Here we go, right? You can see it here, and the rest are the arguments that we're passing to our contract, right? So this is the content of the message, and the first, well, here it's not 20 bytes because we're using ABI decode, but the first value here is the Bitcoin ZRC20 address, and the rest is the destination Bitcoin address formatted as hex. Okay, let's wait for this transaction to be processed, and we'll see in real time when it is. It will show up, so let's wait for it. Okay, we can see that we have two new cross-chain transactions. One is coming from Ethereum testnet to ZetaChain. It was already mined, right? So this is a transaction that called the on cross-chain call function and deposited tokens, and we have a transaction pending outbound from ZetaChain to Bitcoin. So we can use the Explorer, ZetaChain Explorer, to track these transactions. So you can get more information about it. You can see it's coming from Ethereum testnet to ZetaChain, the amounts, the message, and you can also look up the outbound cross-chain transaction. So this transaction is still pending, but we can see it's coming from ZetaChain to Bitcoin. And you can also verify that it decoded the receiver correctly. So it's the same exact address that we have in our balances. So let's query for balances again. So 25TX, so it decoded the Bitcoin address correctly from the message. This might take a bit of time, but once that's done, you will see an outbound mined status, and you can check your Bitcoin balance. You will see it increased because the swap was correctly processed, and now you've swapped one token to another. So let's review what we did so far. So we cloned a template from ZetaChain GitHub repository. We used npx hardhat Omnichain command to create a new Omnichain contract. We modified the logic of the contract to decode values correctly if it's coming from Bitcoin or if it's coming from an EVM chain. We used a swap helper to swap tokens from one token to another, and we withdraw tokens correctly, calculating gas. So if you want to learn more about how to do this and review the code, you can go to ZetaChain docs and go to Omnichain contracts section and click swap and review the documentation here. So it also includes information on how to interact with the task. Thank you so much for watching, and see you in the next one.